Hello, I'm Mick Franzen, a mechanician in the student machine shop in the mechanical engineering department here at UC Berkeley. Today we're going to show the students how to manufacture this small aluminum part that's essential to their completion of their safety certification training so that they have permission and credibility to be able to work with our power tool machine tools in our shop here. Let's have a look at the part itself on a drawing. We're going to take and cut off a piece of aluminum at 1-inch diameter stock, and it's going to be an alloy of 6061 T6. We're going to use a horizontal bandsaw to cut the length a little longer, they call it the rough length, than the finished part, machine part. When we're through with the cutting of that on the horizontal bandsaw, we're going to remove the sharp burrs off of the edges from the part with the belt sander. And at that point, we're going to plan to check ourselves on a lathe using tool checks, and we will move over to the tool support center and get the appropriate tooling for producing the end of the part for the tapped hole. So what are tool checks? We have what we call a tool check system here. We have these brass tokens here. We have them alphabetized from A to Z. There are 14 of them. We use a student's Cal ID card. You will need this to come in and use our tools in the tool check system. My name is Franzen, so I'm going to use the letter F to help me remember which tool checks I used. And I'll count those by weight because it's an efficient way to do it. 60 grams tells me they're all there. And at this point, I'm going to check myself out of the lathe so that portion of it is complete and I can move on. And one thing about our tool checks, it's not a self-serve cabinet, so you need to ask one of the staff members to check these out to keep the machine tools and the tool checks becoming very confused. So please ask a staff member when you need to check out some tools. And safety, as a reminder, is our #1 priority here. You must wear your safety glasses. You must have closed toe, no open toe shoes, flip-flops, or sandals. All long hair, jewelry, anything that can get caught in a machine must be constrained or removed. So we want you to be safe in here. We're now going to cut off the part using the horizontal bandsaw. The first thing we do is to make sure that we have the proper size and the proper alloy, and it's indicated on the side of the part here, 6061 T6 aluminum. We're going to turn off the valve that feeds the hydraulic cylinder, raise up the part physically, and move the part into a preset stop. We will then take and tighten up very tightly the jaws to keep the part from turning while we're cutting it. And before I turn on the saw, I'm going to double check the length to make sure that it's less than 2 inches but more than 1 7/8. So at this point now, we turn on the power and we turn on the coolant. We want to wait for the coolant to come all the way from the sump up through this fitting and in here so that we have what we can see coolant on the blade. Then we open this up, making sure that this is tight, and we wait for it to cut. While the student's waiting, you can use a rag, and we can use that to wipe the part off when it's completely cut off. The switch will shut itself off automatically, so once the part is cut off, I'll catch it with the brush. And at the same time, I'll make a quick clean off of the part. Now you can see it's quite messy, so we can wipe this off. We have sharp burrs, and we want to remove those on the belt sander. But first, let me remove the stock and put it back into position where we had it before, and we'll wipe it off, and it's ready for the next student. Now we're going to use the belt sander here. The belt sander, we're simply going to put the part down flat, turn on the sander, cut off this edge, sharp edge, and the second end, and it's complete. And we can actually wipe off our belt sander as well. So the part is now rough cut to length and is deburred, and so we're now ready to move on to the tool support set and pick up our drill and our tap and our T-handle tap wrench and move on to the lathe. And now we want to select our 1/4-20 tap block set and our T-handle tap wrench so that we can appropriately drill and tap the hole in the end of the part. And at that point, we will use our tool check for the drill and tap block set, and we'll use a tool check, and we'll put that on the hook of the T-handle tap wrench. Now we know where our tools are to be returned, and we can manage our tools appropriately. We're at the lathe. We've selected lathe L5. We want to make sure our key matches the lathe we're going to use. We've put our tools that we've already selected from the Tool Support Center on the top of the headstock. And we have our part here that we're going to insert into the chuck, and we will stick it out about half of the length, and we'll use the chuck key that has a spring-loaded safety device in it so that the chuck key will not stay in there, and it's a dangerous thing to leave it in, so this will not allow that to happen. So we can put this in position, and we want to secure this very, very tightly. So use your shoulders and muscles to tighten up very carefully and very tightly so that this cannot move. Now, let's move to the tool cabinet and use your key to make sure that you have the correct cabinet here. Notice we have charts. In this case here, let's select the spindle speed for our part. Our part is made of aluminum, and the working diameter is 1 inch, so we're going to run that at 915 RPMs. We'll also select the two tools we're going to use, the turning and facing tool and the chamfering tool, and we can put the chamfering tool on top. We're going to locate the turning and facing tool on the top of the tool post and secure it very carefully. Now let's select our speed. We want to turn on our main power here. This light will come on. This is pointing to 915. We can push this in high. The letters and the numbers are color coordinated. And make sure that the chuck can spin. We can jog it. And then to make the lathe run continuously, we can actually actuate it, raise this up to turn it off. We can push it down to neutral and then use the safety brake. We're going to create an 812 thousandths diameter on our part, and it's going to be 625 thousandths long. So we need to calibrate our digital readout so that we can control the accuracy of our part. So with our tool in place and securely fastened, we can crank in on the tool and touch the end of the part. Now in the digital readout, we're going to, in the Z-axis, zero that. Now in this case, we want to remove this rough saw cut, so we'll move it to the left about 12 or 13 thousandths and re-zero it. That is now our datum point. Now we want to calibrate the X-axis, so we bring the part and touch the tool to the part, and it's a 1 inch diameter part, so we're going to use a preset function, and the digital wants to know which axis we want to preset. We're going to preset the X-axis, and conveniently it comes up 1.0, or we could put in 1.0 and enter, and now the digital readout knows that the tool is touching a 1 inch diameter. Now we're going to produce this end configuration using a rough and a finish pass, and that enhances the efficiency of removing a lot of material quickly and giving us an accurate part result. So I'm going to turn on the part, making sure this is tight, and I'll set this to my 0 in the Z, and we'll crank this in and remove that face. Now we'll also move in approximately 625, but a little less than that, and make a mark so that we have a visual that we don't go too far. Now we're going to rough this out in 2 passes, making our X a little less than 1 inch, and we're going to move it in short strips so that we can have a short chip breaking off instead of a long chip. So we can come in and make it into another rough pass. I'll actually use 3, take it down to about 840 or so. And then we can set this up to our 812, which is our finished size. And we'll go in very slowly and smoothly and create a very accurate and smooth finish. Take it into our negative 625. And we'll rotate this out, and we have it completed on the facing and the turning. Now we need to chamfer the edges and remove these sharp edges here. So we will remove the facing and turning tool, and the chamfering tool goes on the back side, lock it down. Again, we'll turn it on by raising it up, and we're going to just remove the sharp edge so that it looks appropriately. We're not going to hold you to a tolerance at this point, so that it's completely removed on both edges, and we're finished there. Now we're going to drill and tap the hole in the end of the part. We're going to use a number 4 center drill. We're going to use a number 7 tap drill, drill 3/4 deep, and then we're going to tap this by hand using a T-handle tap wrench and tap it a 1/2 inch deep. So at this point, we need to load the center drill, which we have from our tap block set, into the drill chuck. So we can release the drill chuck key, tighten this in position, and then use our key to tighten this up so that the center drill does not move. Now the tailstock is all manually operated. To move it back and forth physically, you have to move it. To constrain it so it doesn't move, we use this clamp. Now it will not move. If we turn this in, 10 of these turns makes 1 inch, so 1 turn is 1/10 of an inch. And we have actually a very accurate dial here that you can move this in at 1/1000th of an inch at a time. This lever here locks the quill so that it can't move. We want it to be unconstrained. So we'll turn our part back on, bring the lathe up to the part, constrain it, and we're going to go in about 1 turn, 2 turns, about 3 turns is about appropriate for that particular. Then we can remove the center drill and we'll install the tap drill. Now the tap drill, we want to make sure that we tighten this very securely because it could otherwise spin in the chuck. So make sure that it's adequately tight. And then we can move this up to where the drill is just entering the part and then constrain this down. We always want to use a little bit of oil on our drills and center drills. It keeps the aluminum from sticking to it and makes the chips flow easily. We're going to turn this in about 3/4 of an inch, which would be about 7.5 turns. So we turn on our power, 1 turn and stop, 2 and stop, 3 and stop. That breaks the chip 4, 5, 6, 7.5, and that gives us our 3/4 of an inch, and it's automatically measured for depth. Now we want to take and tap this hole using a tap, but we're going to do the tapping manually because trying to do it under power takes a lot more experience than most of our students have. So we'll also use what we call a tap guide in the tailstock to make sure that our tap is entering accurately into our part. So the first thing we want to do is turn off our power so that we can't turn this on inadvertently. We'll mount the square shank in the square socket, and we will constrain it by locking it clockwise, and then we can put this in position and align it with the center aligning tool. We also again want to add some oil so that our tapping is done easily, smoothly, and keeps our taps nice and sharp. Now we're going to go in 1/2 inch. This is a 1/4 20, so that means we're going to turn this in 10 turns, or half of the 20. So we'll turn it in 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's a 1/2 inch deep, and then we'll back it out. It takes a fair amount of force, and I think the experience of tapping by hand is an educational experience into itself to realize there's a lot of force going on in machining and manufacturing. When we're done, we can take and wipe off our tap, remove the tap, put it back in place. We'll remove the spring-loaded center of the tap guide. Now, before we remove the part, we want to make sure, have we removed the proper amount of material, and have we turned and faced it, chamfered and drilled it and tapped it? And we have. So let's remove this from the chuck. And what we need to do is we need to measure the overall length of it. Now with the part removed, we can measure the overall length of it, and it's 1 inch 930 thousandths. So we'll remember that. And we can put that back into the lathe because we want to remove this rough cut and bring it to the proper length. So we'll tighten this up securely again, and we're going to use our turning and facing tool. Again, put it in place. We'll move this out of the way. We can come up and touch the end of the part, and you'll remember that we're touching a 1 inch 930 thousandths length, so we can preset our Z at 1 inch .930 and enter it. And now the digital readout knows how long the part is, so we turn our power back on, turn the spindle back on, and we can move this to about 1/893 and make a rough pass across here. And then we'll come make our finished pass to our dimension is 1/875. And so we'll cut it right at that, even though there's a tolerance of plus or minus 15 thousandths or so. Always use your brush to remove chips from your parts. Don't use your fingers. It's not. It's dangerous. It's not a good habit to get into. Now we'll use the chamfering tool, which has a 45-degree angle on each side, just to remove the sharp burr on the edge of the part. And basically, that's all we have to do. And our part now is turned, faced, chamfered, drilled, and tapped, and it's cut appropriately to the proper length. And we can remove the chips out of the center part there. And then the next thing is to make sure we clean up all of our tools and our parts, put our tools away, return all of our tool checks. Now for cleanup, we basically can sweep everything down into the chip tray, and then we can empty the chip tray and make sure that everything is cleaned off here. Then we can take and empty the chip tray, which is removable. And we can dump that in our aluminum only bin and recycle all of our chips. We also want to replace our tools. We can use an air hose to blow off the tools. We do not use the air hose to blow off the lathe because it can blow the chips into the lathe. Only to the tools themselves. And we'll turn off our machine down here, the main machine switch, put this in neutral, and then we will return all of our parts and our tool checks, taking our drawing with us, turn off our light, and oftentimes we'll just take and do a little quick wipe down here, and we're ready to either use the lathe again or the next party can use the lathe as well. And we'll return these at this point back to our tool support system. After we've completed the lathe portion of our small phase 4 part, we will take and, having cleaned up our lathe and put our tool checks away and all of our tools that we've used, we'll take and get our lathe key and exchange it at the tool check cabinet for a mill key, which I've already done. You will do that with a staff member. Students are not allowed to make the exchanges for the interest of keeping that cabinet organized. So I have a mill key. Mill 4 matches mill 4, and at this point we're going to take this finished part as an example, and at the mill we're going to produce the flat and the two holes in accurate locations. In order to do that, we have the sample that we cut on the lathe, and we're going to position it, and I'm going to use some tools inside the cabinet here, a V-block, the end mills that we'll typically use, and the edge finders. There's a little piece of paper here, and there's a file here that we're going to use, and we'll show you how each of those is used. We will use the V-block to position the part such that we can accurately locate the axis, and we can actually hold the part above the base of the mill vise so that when we drill our holes it doesn't drill into the top of the vise. So make sure there are no chips or metal shavings in here, otherwise we have not an accurate position. Place the part inside and contacting the stationary vise jaw. And you want to tighten this up about 30 pounds of pressure on here to constrain this so that it can't move while we are machining. Now we're going to take and cut the flat first. The flat is about 1/2 of an inch long, and it's 1/8 of an inch or 125 thousandths deep. To do that, we'll use an end mill. The end mill we'll select will become from one of these tools that's inside the cabinet here. We'll use a end mill that's about 1/2 of an inch or about the same size as the flat. To mount the end mill inside the milling machine, we use what we call collets. This is an R8 collet. We'll match the size of the collet to the shank of the end mill, and it has to be a perfect match. And we'll slide the end mill up where the flute beginning just goes into the collet so we have a very, very firm grip. Now there's a slot here that corresponds with a little pin inside the spindle, and we'll rotate it so they coincide. As I push this all the way up, there's a drawbar up here that screws into the back end of the collet. I'm going to tighten that up, and I'll use a wrench that we keep on the side of the mill with the collets in the tool check area, tool tray area. And I'm going to tighten this up clockwise as I look down on it. I have a brake here that I can firmly hold the spindle in position, loosen the brake, and then I can tighten this back up. Now, in this case, we have the position is in low here for low gear. To change from high to low, when we change speeds on this, the machine has to be stopped. So it is in low, I'm going to put it back into high. Sometimes this doesn't go in easily, so we rotate this spindle by hand and make sure it goes into position. Now, how fast are we going to run our end mill? We look on the chart over here. This is about a 1/2 inch end mill. The aluminum is what we're cutting, and we look at the 1/2 inch, and it says about 800 RPM. That's an estimate. We could run it maybe 1,000 or 600, depending on how deep or how heavy a cut we have. Now, we want to take and calibrate our end mill from the top of our part and from the end. So we'll make sure that the clamps are loose here so that we can move our table over into position. Now, for the depth of this, it's going to be 1/8 of an inch or 125 thousandths. So we're going to cut that in 2 steps. We're going to cut it about 100 thousandths for roughing and then 25 thousandths to complete the 125 thousandths for our finished cut. We rough and finish because the roughing gives us efficiency and the finish cut gives us accurately and smooth finish. So if I turn this 10 times, the entire mechanism or the table and the knee all move up 1 inch. So 1 turn is 1/10 of an inch. I'm going to turn this so that there's a 0 point right here with a little index mark so I know a baseline where I'm located on my z-axis. Then I can loosen this quill here. This is a quill clamp. Bring it all the way down, and I'm going to just touch the top of the part with the end mill. And when I touch the top of the part, I'm going to constrain that quill so it can't move up. If we don't constrain it, it will move as it likes. So we touch the top and tighten this up firmly, and then move off. Now I can raise this up 1 turn, which is 100 thousandths, and I'm located at my rough depth. Inside the drawer, we have these little pieces of paper. They're about 4 thousandths of an inch thick, about 1/10 of a millimeter, and so we can use that to find the edge of our part because we want to index the edge of the cutter to the part to be able to cut the 500 thousandths. Let's check our speed. We're in high, and the switch over here says high, pushing it up, or low, pushing it down. You need to remember high to high and low to low. So if this is in high, we turn the switch to high. If this is in low, we turn to low, and that makes the end mill turn clockwise. It's an appropriate rotational cutter direction that we use for most all of our taps and our end mills and our drills. So remember, high to high, low to low. So now once I have it in high, I turn it on, and I'm going to run this down to about 800 RPMs. Because that's what our chart recommends here. This is the brake. We can shut that off and stop it for cutting the noise down a little bit. So I'm going to take this piece of paper and just gently bring it up close to the edge of my part. And when it touches the paper, it'll pull the paper from my fingers and pull that right out. Now I know I'm within 4 thousandths of the edge of that part. So on the x-axis, I can 0 that. And I can move an initial 4 thousandths to compensate for the paper and 0 it. It doesn't need to be that accurate. Now we need to cut the flap so that this line here is a straight line. So if we cut in from this angle, we'd have a curve. And we may go beyond our 500 thousandths limit. So we'll move the part away from the end mill, and we'll move this down to about a negative 480 or so, something less than 1/2 inch. 477, and we're going to constrain this x-axis. If we don't, it can't float. So we need to constrain the x-axis, constrain the z. Now we're set up in our rough configuration. We're going to be almost the depth we want and almost the length. So now we can turn on it high to high, and we're going to conventional mill cutting across here, and it just cuts that material off really easily. I like to turn the mill off when I'm going to change the table position so I don't hit any of the parts of the mill while it's running because it'll damage the cutter and damage the part. If it's not running, we typically don't cause a lot of trouble. So I'll set this at 500 thousandths, and I'm going to raise this up to another 25 thousandths, and we can store this back here if it's in our way. We'll turn this on, same speed, we're going to climb mill it back. Climb milling it gives us a nicer, smoother, burr-free finish. Turn it off, use our brake, loosen the clamp, bring it up. Now, I have a little burr on this edge here. I know that from experience, so I'm going to take the file and I'm going to carefully not touch that with my finger while I'm filing. I'm going to file off the edge here and file off the little burr here, and now our part is cut and the flat is the right size and the right depth. Now to remove the end mill, we basically have to reverse our operation, which means I have to put the brake on with my left arm, pull it back, and I'm going to loosen the bar up on the top here one turn. And our end mill is still constrained and stuck in there. So we'll take this little brass mallet and we'll give it a sharp tap and it unlocks the collet. R8 collets are locking collets. We can take a rag. Be careful because this end mill is sharp. So be careful when you're cleaning it off that you don't cut your fingers. Now we're going to take and put a drill chuck into position so that we can drill the holes. And in this case here, the holes are going to be datum from the end of this part of the part over 1 inch from this edge and over 1.5 inches from this edge here on the center line of the part. So we'll put the drill chuck in there, and to do that we're going to loosen up the collet. You can see it's coming out and it's going to drop out in my hand, and we'll replace it, and then we're going to use a larger collet that fits the 3/4 inch shank of the drill chuck. This diameter and this diameter have to match precisely. So I'll mount this in first because it's lighter and the chuck is heavy, and I'll tighten this up and we'll move this off. We'll loosen this one as well. You have to remember to loosen your clamps, or it's like driving with your parking brake on. We'll put this up in place. Remember, it's heavy, so we have to tighten it tight, and I'm going to hang on to it with my left hand, tighten with my right, and then use my brake, and I've got that drill chuck constrained in there and it's ready to go. Now, I need to drop the table down just a little bit because the chuck is much longer than the end mill was, so we'll drop it down here about a couple of inches. Now, to find the center of our part, we're going to use what we call an edge finder. It's a very clever little device. It's a floating spring-loaded device. The diameter of this is 0.2 inches, 200 thousandths. And knowing that's 200 thousandths diameter, the radius is 0.1. So we're going to actually position this in, not as a cutting tool, but as an indexing tool. And we'll use our chuck key to hold it in place. Never leave a chuck key in the chuck when you're setting up, because if you have to turn it on, it launches and becomes a very unsafe projectile. Now, we'll look at our chart, and it says edge finder runs at 1,200 to 1,400 RPM. So make sure we're in high, turn it to high, and then once this is engaged and we're running, we can change our vary drive to bring this up to about 1,400 or 1,200 RPM. That's the RPM that works best. It's supposed to flop around like that. So what we can do is bring this down and come up close to the edge of our part, and we can turn this on. Now, a close detail will show that when we get up close to this, it gets very, very still. And at the point where it makes full contact, it will move laterally off the part, and that'll be right about there. So at that point, we know the center line of the spindle is exactly 0.1 inches to the right of our part. So we can actually take and zero the X, raise this up, and move it over the radius, which is 0.1, in the negative direction. Have to get it to there. And then we're going to re-zero this because our datum point is right at that edge. Now the first hole is going to be, I'm going to move back 1.5 inches and make that our first hole. And now we need to pick at the center of the part. We know that the part is 1 inch, so if we can accurately index this edge here, which is tangent with our part, we can move over the negative 0.5, which is a 1/2 inch. It's the radius of the part. So we'll bring this down and move over and just barely touch the edge of the vise, and at the point where it just contacts it, moves to the left. And in this case here, this is the y-axis. So again, I can raise this up, I can move this back 0.1, and that's in the positive direction of the Cartesian coordinate system here. And then we want to re-zero that because that's our data point. We'll move in the negative direction at a 1/2 inch, which is half of our 1 inch diameter. So it's a negative 0.5. There we go. And we're not going to we're going to ignore that that digit there because it's not significant. It's a half a thousandth, and we're not trying to be any more accurate than that. Okay. Now, we're going to remove this. Again, do not leave the check key inside. And I've already selected, using my tool checks, a number 4 center drill and a letter F drill. How do I know those are the right ones? You'll just look on your drawing and it tells you. Start with the number 4 center drill, and then we'll drill through with the letter F drill. So everything you need to know is on your drawing. Actually, there's more information on the drawing than you would typically get in a machine drawing. So we're going to grab onto the center drill, put it up inside here so we have a good grip, meaning a good friction grip. We need to tighten this up because most everything we fasten here is held by friction. So we have another tool in here. So we're going to slow this down to about 3/8, which is about what that size is, to 1,000 RPM. So again, high to high. Let's take it down to 1,000. And I'm going to come down and just make a little mark. Notice I can change position of this handle by moving this out. I'm going to make a little mark. And I'm going to take my scale and just double check to see if from that edge of that hole to the center is 1.5 inches. I'm looking to see if I forgot to compensate for the 0.1 edge finder radius. So we look good there. So I'm going to come down and I'm going to drill the hole, but I'm going to pre-chamfer it because I know the hole is this diameter. I can use the shank as a gauge. And that diameter of that center drill is about a little bit larger than this, so I like that. I want to be able to constrain that and fix it so we can actually push down while it's not running. And there's a little quill stop here that we can push in, bring up, and it's threaded so we can lock it in place. Now I can come down and touch that. If I want to go a little more, I can bring it down to the threaded portion. And now I've got a pre-chamfered center drill, and we'll move it over to 1 inch on our x-axis. Right there, we can just snug that up a little bit. And we'll do the same thing here. Now I could put a little bit of oil on that. It always helps to put a little oil in it. Keeps the chips flowing. And then it hits my stop here, and I'm at the depth that I want to be. Now I may have to drop this down a little bit because our drill is a little longer than our center drill. Again, we're going to loosen up the center drill. We can take and wipe it off. Always keep your tools clean. Chips and steel metal shavings are the nemesis of precision manufacturing, so you want to make sure everything's clean. Also, you want to grab these drills into the solid part. That's the only part of the drill that's actually secure for constraining it. Now, I'm going to bring my part down, the drill down to the part. I know it's 1 inch, so I can guesstimate that it's about 1 inch. And if I put this about that distance, when it goes through the bottom, I can tell when I'm going to reach the bottom so I don't hit the vise after I go through the bottom part of it. You can put a little bit of oil on it. We do a little kind of a pecking, and then we pull down firmly, let the chips out, pull down firmly, let the chips out. Notice I'm coming close to the bottom. I can bring it down a little bit more, and it's just dropping through, and I can feel it drop through. Now, there's some chips in here. Always use your brush. We'll take and bring this over to about 1.5 inches, and we'll do the same thing. Come down through here. We'll put this little oil in there if you want. And again, we see when we're coming through here, we go lightly. If you want to go through a little lightly, you get a really small burr on the other side. And we basically completed our part with the exception of deburring the holes on the opposite side. So in this case, we can rotate our part 180 degrees and use our drill to line up our hole so that we can now put the center drill back in and we can chamfer that hole. Again, watch out for these chips. They are potentially sharp. Aluminum is not so bad. Stainless is terrible, so just be careful. Tighten this up again. Now the trick here is not to cut the chamfer too deep. So what we typically do is bring the part down and the center drill down and preset our stop so we don't go too deep. Turn this on, I can come down and it will limit how far I go into the part. We can come down and touch a little bit more, a little bit more. And now that's preset and that looks really good. And then I can come over to my 1 inch. We just want to touch it and get out of there. We want to have only about 3 or 4 revolutions before it cuts the burr off. Then we can take our air hose, blow this off. We can also use the air hose to clean up our end mills and our drill. Reverse order there. We never use the air hose to blow the chips away from the milling machine because it blows the chips underneath and it can damage the machine. So at this point, we've got our part completed. It's been turned down and chamfered, drilled and tapped in the lathe, the flaps cut, and then the two holes have been drilled appropriately and accurately, and your part will come out just like this when you complete your phase 4. Again, I'll take and clean up all of these chips. We can use vacuum. Vacuum is a very effective way of cleaning our chips up. It's very noisy. And then for the floor, we can put the attachment on and we can vacuum the floor. And I will do that in just a few minutes. But basically, we also want to take the drill chuck out, put our center drill back, reclaim our tool checks, and I'm going to remove this. Sometimes we put this in low so I don't have to use the brake. I'm short, so I have to feel for that hex up there. Loosen it one turn, it's stuck in there, give it a tap, and it comes right out. We usually put the drill chuck key and the drill chuck together because they're kind of married. One doesn't work very well without the other. And we remove the collet. Last thing we do in addition to cleaning the floor, cleaning the front area and all of our tools is loosen all of our clamps so that the next time you or the next operator comes in to make the part or make some of their machining parts and so forth, it's ready for you to go. So this would complete making your part for your phase 4 part.